All right, section 3.4 is on what's called the chain rule, which honestly might be like the most important thing we've learned in the first half of this semester. It will also be really important for the second half of the semester. So this is going to be big for the test, knowing the chain rule. And it says, first we're going to develop a pattern just like we did with the product rule, and then we'll use the pattern to help us in later problems. Okay, so the first thing is here's h of x, and they want us to find h prime. And we have not seen parentheses to a power yet. Well, you could write this set of parentheses out twice and do FOIL and then find the derivative, but I am going to write the set of parentheses out twice, but instead of doing FOIL, I am going to use the product rule, thinking of this as my u, and then the second one as my v. So yes, they would be exact same thing, but I'm just going to use the product rule on that. So h prime. So remember, the product rule is u times v prime, so u is that. And then v prime, so the derivative of what's in here is going to be 8x plus 0, and just 8x. So there's u times v prime plus v, which is that, times u prime, which is also just going to be 8x. Okay, well, these are exactly the same. So think of, like, say that whole thing is w, right? So basically we have w plus w, which would just be 2w, right? So I'm going to just add them together like that, like we'd get 2w. So 2 times this. Okay, so now let's look at if we have that set of parentheses cubed. So I'm going to write it, I'm not going to write out all three of them. I'm first going to write 4x squared plus 8 squared, and then the one left over. And I'm going to use the product rule again, where this is my u, and this is my v. So h prime of x is u times v prime, so u times v prime would be 8x plus v times u prime. Okay, well, here's u, which is exactly what we had in the first one. So u prime is this. We just found the derivative of that. So 2 times 4x squared plus 8 times 8x. Okay, so I am going to rewrite it slightly. So I'm going to leave the first half just like it is. But then I'm going to multiply these two together and just write it as that parentheses squared. I'll have the 2 in front. So 2 times 4x squared plus 8 squared times 8x. And so now I'm basically doing the same thing I did in the last one, thinking of this whole thing as w plus, and so this is the same as that, so it's like 2w. W plus 2w would be 3w. Right? So I have 3 times this whole part. Okay, one more. So this has us do to the -1 power. Okay, well, I can't like write out the parentheses twice. -1 means it's in the denominator. Right? So it would be 1 over 4x squared plus 8 than just to the first power if I put it in the denominator. So now I am using the quotient rule to take the derivative. So this is my u and that's my v. And so remember, the quotient rule is start at the bottom. V times u prime minus u times v prime all over v squared. Okay, v is the bottom times u prime. Well, if u is 1, then u prime is 0. The derivative of the constant is 0. Minus u, which is 1, times v prime. So if v is the denominator, v prime is 8x. All over the denominator squared. Okay, well this one is times 0, so that whole first term is gone. So we have, I'm just going to leave this negative 1 there, so I'm just going to write it as negative 1 times 8x over 4x squared plus 8 quantity squared. And then I'm just going to write it, so that it looks a little bit different over here. So I am going to leave the negative 1 first. I am going to put the 8x last, just because we've had the 8x last in the other two. And I'm going to bring this up to the numerator. So then it would be 4x squared plus 8 to the negative 2. And then the 8x again. So we should be able to see the pattern now. So look at this first one. Look at the numbers out in front. 2, 3, negative 1. Where did the 2, 3, negative 1 come from? Those were the powers on the set of parentheses. Notice the stuff inside parentheses stayed the same. And what about the new power on the parentheses? So it was negative 1, now it's negative 2. It was 3, now it's 2. It was 2, now it's 1. So it's almost like when we had the power rule for x, we bring the original power out in front. This time we're leaving that stuff alone, subtract 1 from the power, and then here's the extra part. Multiplying by the derivative of what's inside parentheses. That's where the 8x came from. Always the derivative of what's inside the parentheses here. Okay, so it says the chain rule applies whenever we want to find the derivative of a composition of functions. So composition just means there's an outer function and an inner function. Sometimes there's more than just two. There might be an outer, a middle, and an inner. There might be an outer and then like 3 inner, or 3 middle and an inner. So here it says, how can we write this as a composition of functions? G and F, where F is the inside function and G is the outside function. So F is, like if you have parentheses, F is going to be what's inside parentheses. So in our problem, f of x is the 4x squared plus 8, the stuff inside parentheses. And then g of x is the outside function. Well, what do we do after 4x squared plus 8? Well, then we cube. So g of x would just be the cubing function, x cubed. And then if we have our original function h written as that composition of two functions, then h prime, so here's the function notation for the chain rule. So you take the derivative of the outside function, leave the inside function alone, then at the end multiply by the derivative of the inside function. It says, does this rule fit what we found on the previous page? Well, let's try that. So if g of x is x cubed, what's g prime of x? Well, the derivative of x cubed, this is just power rule, 3x squared. And what's f prime? Well, that would just be 8x. So then let's look. What is g prime of f of x times f prime of x? Well, with composition of functions, you have to work from the inside out. So I am going to replace f of x with its like formula. So g prime, and so in place of f of x, I'm putting 4x squared plus 8. So I'll do that, and then times f prime is 8x. Okay, so g prime of 4x squared plus 8. So this 4x squared is the new input. So it's going where I used to have x, right, in g prime's formula. So g prime says do 3 first, and then the input squared. Well, the input is 4x squared plus 8 squared, and then at the end we have times 8x. This is exactly what we got on the front page. The power came out in front, leave the inside alone, subtract 1, multiply by the derivative of the inside function. Okay, that's function notation. I also want to introduce you to the U substitution. We've seen it already with product rule and quotient rule, right? The UV for the product and the UV for the quotient. So we've already seen examples where we use U and V instead of functions. This is going to be more important in the second half of the semester, that we get used to this U substitution. It's going to come back to us in chapter 5. So let's look at an example. Follow these steps with this function using U substitution. So it says, let U be the inside function. So our function here, this is not a product. This is not multiplication. In fact, if you had secant by itself, that doesn't even make sense. Secant needs an input. So secant what, right? It would be like if I wrote f of x equals square root, right? Square root of what? You need an input. Same thing for the trig functions. You can never write just cosine with nothing after it. That doesn't make sense. So the inside function here is tan x. So I would say let u equal tan x. And then I always, as soon as I identify the inside function, I know I'm going to need its derivative at some point. And I'm using this Leibniz notation, and it sort of looks like multiplying and dividing by the same thing, right? We had dy dx. It looks like we multiplied and divided by du. So these are derivatives treating other letters as the variable. So we're always going to have a d something. So you're going to have d's in the numerator and denominator. The variable that goes in the top is the one on the left-hand side, so u. The variable that goes in the bottom is the one on the right-hand side. So in this case, it's x. And then you just take the derivative of this expression. So what's the derivative of tan x? So remember, that was from the previous section. That's secant squared. And we don't use this yet. We'll use this at the end. I just want to do the work as I go along. Okay, so now it says rewrite y. So once you identify the inside function and its derivative, I always do that, then I rewrite y. So now, how can I write y? So u was tan x, so wherever I have a tan x, I'm putting u. Right? So y is equal to secant u. I want to get to a point where y, when I write y, there is no composition of functions anymore. There's just one function. Once you get y down to one function, then you won't have to do any more steps of the process. And here there's just one function, secant. So I am going to take the derivative of both sides. So d something, d something. The one in the top is the variable on the left. The one on the bottom is the variable on the right. And what is the derivative of secant u? Again, that's from the last section, secant u tan u. Once you get y in the numerator, that means you're done and you're ready to apply the chain rule. Okay? So the chain rule says, so the original equation had y on the left, so dy and x on the right, dx. And now we just go back through the derivatives. We go back through the derivatives we found. If I didn't have the paper up far enough, I'm just going to wait a minute in case you need to get this written down. Sorry, I missed that it was going out of the screen. Okay, so just multiply the derivatives we found together. So dy du times du dx. When you're done, it should look like if you canceled, you'd get the left-hand side back. Yeah, and so like if I were to cancel the du's, we'd get dy dx. But now we're going to substitute in what they're equal to. So dy du is secant u tan u. And I know this looks really complicated, but once you do a few, it's not so bad. And the process starts to seem a little more understandable. And then du dx is secant squared. So it says find the appropriate derivatives, but I did that as we went along. And then substitute back in wherever you have a u. So you should look at your original problem started with y's and x's. So your final problem should only have y's and x's in it. So we don't want u in our final answer. So I just substitute back in for u. So u is tan x. So secant of tan x times tangent of tan x. And then at the end times secant squared x. Okay. So this is our final answer for that problem. We'll do more examples so you see kind of how it works. I'm actually, on the next page, I'm going to do this problem before I do this problem. This one is tricky because we have to use the product rule and the chain rule at the same time. So the second one, we only have to use the chain rule. And it says use the method of u substitution. So the first thing I want to do is identify the most inside function. And so I see there's stuff inside parentheses here, 1 plus cosine 2t, but even with that, cosine, we know the derivative of cosine t or cosine x. This time it's not just t or x, it's a 2t. So actually that is our most inside function. So I am going to let that be my u. So u is going to equal 2t. And as soon as I identify my inside function, I also say what its derivative is. So it's d something, d something. The variable on the left goes in the top. So du, the variable on the right goes in the bottom, dt. And what's the derivative of 2t? Oh, it's just 2. And then, remember, once you have identified the function and you take its derivative, then you rewrite, so u equals 2t, you rewrite the original function using your substitution. So wherever I have a 2t, I'm plugging in u. So now, y equals 1 plus cosine u to the negative 4. And then you ask yourself, do I still have an outside function and an inside function? And yes, we do. And so I usually use v as my next letter. And this one I can just use the sum rule, right? I just want to make sure it's not a composition of two functions. Like inside parentheses, that's just sum rule. There's not an outside and an inside. So I'm going to let that be my v. So let v equal what's inside parentheses, 1 plus cosine u. And as soon as I identify that, I take a derivative. The variable in the numerator is what's on the left. The variable in the denominator is what's on the right. So dv du. And then what is the derivative of 1 plus cosine u? 1 plus cosine u. So the derivative of 1 is 0, and the derivative of cosine is a negative sign. Okay, and now wherever I have 1 plus cosine u, I'm going to replace that with v. So now, after you take the derivative, now you go back and rewrite the function again. So now, y is equal to, this whole thing is being replaced with v. So v to the negative 4. And now it's just power rule. There's not an outside function and an inside function in this, so I'm ready to take the derivative. And the variable on the left is y, so that goes in the top. The variable on the right is v, so that goes in the bottom. And then it's just power rule. Negative 4v to the negative 5. Remember, once you get y in the top, then you're done. You're ready to apply the chain rule. So the chain rule says d, so think about how the problem first started, when we were first given the problem. Y was the variable on the left, so that goes in the top. T was the variable on the right, so that goes in the bottom. And now go back and multiply the derivatives we found together. So you ended with dy dv. The one before that was dv du. And the one before that was du dt. And if you think of these as fractions, right, the dv's would cancel, the du's would cancel, and you just end up with dy dt. Okay? Now, though, we go back and substitute the functions in for these three derivatives. So dy dv was negative 4v to the negative 5. dv du was negative sine u. And du dt was 2. Okay, but the only variables in my answer should be y's and t's, so I can't have u's and v's in my answer. So I go back and substitute in. So negative 4 v, what was v? Well, v is 1 plus cosine u. That's to the negative 5. Negative sine, what was u? Well, u was 2t. Times 2. I'm going to multiply all of just the constants together and put those at the front. So I'm going to multiply the negative 4, the negative, and the 2. So multiply all the constants together. So that would be positive 8. I still have to get rid of this u, right? I can't have u's in my answer. So it'd be 1 plus cosine, but again, u is 2t. That is to the negative 5 times sine of 2t. The 2 already came out in front. So this is our answer. Alright, so let's go back to the problem that I skipped. And before I even try to use any of the rules, I'm going to rewrite this. I'm just going to write it at the top of the page. So instead of square root of theta, I'm going to call that theta to the 1/2. And then tangent, instead of calling that 1 over theta, I'm going to write that as theta to the negative 1. So I'm going to have to use the product rule, but I'm also going to have to use the chain rule. So first, the product rule. I'll think of this is my u, and this is my v. So then r prime will be u times v prime plus v times u prime. So what parts do we already know? Well, I know that u is secant theta to the 1/2. The theta is to the 1/2, not the secant, times v prime. This, we're going to have to do some work. That's going to require the chain rule because there's an outside function of tangent and an inside function of theta to the -1. And then plus v is tan theta to the -1 times u prime. And u prime, that is also going to require the chain rule because secant is the outside function and theta to the 1/2 is the inside function. So that's where we have to do some extra work to figure out what goes in these two blanks. So u is secant theta to the 1/2 and v is tan theta to the -1. So I think I'm just going to think of using the function notation this time. So we get practice with both. So the function notation says first you take the derivative of the outside function, but don't change the inside function at all. So let's do the u prime. So the outside function is secant. So I want to take the derivative of that. I want to take the derivative of secant, but leave the inside alone. So I'm leaving the theta to the 1/2 alone. And the derivative of secant, remember, is secant tangent. So secant, the inside function stays the same. Tangent. So this part, this is the derivative of the outside, but the inside hasn't changed. Then at the end, we multiply by the derivative of the inside function. So what's the derivative of theta to the 1/2? Well, there it's just the power rule. So it'd be 1/2 theta to the -1. Okay. So that's our u prime, so that will go here. We'll write our answer when we're done finding v prime. So same idea with v prime. So the outside function is tangent. So we want to take the derivative of that, but don't make any changes to the inside. And the derivative of tangent is secant squared. So we get secant squared, the inside stays the same. And then at the end, so here's the derivative of the outside. And then at the end, we multiply by the derivative of the inside function, which is theta to the -1. And there we're just using the power rule. So -1 theta to the -2. Okay? And now we're just plugging those things into these spots right here. So r prime of theta is secant theta to the 1/2 times, and then this is v prime. So right here. So secant squared theta to the -1 times negative theta to the -2, or you could say -1 over theta squared. I don't care how you write it. I'll say -1 over theta squared. So this was u, this is v prime, plus v is tan theta to the -1 times u prime, which is this. This was v and then u prime. Secant theta to the 1/2 tan theta to the 1/2 times 1/2 theta to the -1. And it's not like there are any like terms that you could combine. If you wanted, you could factor out a secant theta to the 1/2, but even if you do, it's not like you're going to be able to combine anything. So I'm just going to leave my answer like that. Okay, I'm going to go back to u substitution with this next problem. And so I want to think of the most inside function in the problem. And actually, before I do that, I am going to do one other thing to rewrite the problem, because it's a mistake that I see people make a lot. Like if you have y equals cosine squared x, a lot of people will say, oh, that's the derivative is 2 cosine x. That's not enough. So a lot of people don't see this as a composition, but if you write it as cosine x and then the whole thing squared, then you're more likely to see an outside function and an inside function. It's pretty easy to see that cosine is the inside and the outside is the squaring function. So whenever I have trig functions to a power, I'll go ahead and write parentheses instead, because that helps you remember the outside and the inside. So instead of tangent to the fourth, I'm going to write tan of that, and then that whole thing to the fourth. So you see the 4 more as the outside function. And then this whole thing to the third power. So here we actually have a lot of inside functions. So we're composing a lot of different things. So this is going to require a few steps of the chain rule. So I'm going to let my u be the most inside function. So I just kind of work my way inside the parentheses. And the one that's most inside is t over 12. So I'll say let u equal t over 12. And remember, as soon as I identify a function, I like to take the derivative. So d what, d what. So the left is u, the right is t. And sometimes when people look at this, they think, oh, I have to use the quotient rule because it's a fraction. But remember, you can write this as 1/12 t, right? You can pull the fraction out in front, so then it's just the constant multiple rule. You don't have to use the quotient rule. So the constant multiple rule says the 1/12 stays out in front, and then the derivative of t is 1. So we just get 1/12. Okay, once I've identified the u and taken its derivative, now I rewrite y. So what does y equal if I make that substitution? And I'm not substituting in the derivative, I'm substituting this in. So where does u go? U goes wherever I had a t over 12, which is right here, or right here, I guess. So let's rewrite y. So I still have parentheses 1 plus parentheses tan u to the 4th, and then the whole thing cubed. So I still have outside functions and inside functions. And so I let v be the next inside function and just work my way inside parentheses. So here's a function inside parentheses. So that's like my next inside function. So v is tan u. And then as soon as I identify that, I like to take a derivative. And so the variable on the left is v, the variable on the right is u. And what's the derivative of tan u? Secant squared u. And now I rewrite y using this, not the derivative, using my substitution. So let's see. Tan, wherever I have a tan u, I'm putting v, and here is tan u. So y is 1 plus v to the 4th, all of that to the 3rd power. There's still an inside function and an outside function. So I'm going to do one more step of the chain rule, and I'll let w be the inside function, which is 1 plus v to the 4th. As soon as I identify a function, I take the derivative. So w is on the left, v is on the right. And what's the derivative of 1 plus v to the 4th? Well, the derivative of 1 is 0 plus, and then the power rule, 4v cubed. Okay, and then now I'm going to rewrite y using this substitution. So w goes in wherever I had 1 plus v to the 4th, which is right here. So making that substitution, now y equals w to the 3rd. And now there's not an outside function and an inside function. There's just one function where I can use the power rule. So I'm ready to do dy, dw. And so it'd be 3w squared. And once you get y in the numerator, you're done. You're ready to apply the chain rule. So let's look at how the problem started. Well, y was on the left and t was on the right. So we're looking to get dy dt. And let's just go back through our list of derivatives, multiply them together. So dy dw, the one before it was dw dv, the one before it was dv du, and the one before it was du dt. And so if these were fractions, you could cancel the dw's, the dv's, and the du's, and you just end up with dy dt, which is what we want. Now let's substitute those functions in. So dy dw is 3w squared. dw dv is 4v cubed. dv du is secant squared v. And du dt is 1/12. Okay, I like to just multiply all the constants together. So let's see. 3, 4, 1/12. Well, 3 times 4 is 12. So I have 12 times 1/12. So the constants just kind of all cancel. We get 1. But I can't have w's, v's, and u's on the right-hand side. Everything has to be in terms of t. So let's substitute back in. So w. What am I putting in place of w? Well, w is 1 plus v to the 4th. So I have, and remember the 3 is gone. So 1 plus v to the 4th is w, and that's being squared. The 4 also canceled. So v cubed. V is tan u. So tan v cubed. Secant squared u is t over 12, or 1/12 t. And then the 1/12 is gone. Those constants multiply together. So, okay, I still just have to get rid of the u and the v, so the secant squared part is fine. So 1 plus, what's v? Well, v is tan u. So 1 plus tan u to the 4th. And then tan this cubed, or now you can call it tan cubed because we don't need to take the derivative again, so I don't need the outside and inside to be as obvious. U is t over 12. And then secant squared, t over 12. And then the last thing is just to replace this u with t over 12. So I'm just going to call that tan to the 4th, t over 12. But again, you can write it as tan of t over 12 and then the whole thing to the 4th. Either way is fine. Oops, this is still supposed to be squared. I left that off. Sorry. 1 plus v to the 4th, whole thing squared. And then tan cubed, t over 12. Secant squared. T over 12. All right, and that's our answer. That's dy dt. Okay, the next problem. So use any method. Well, think about the rules we're using here. Hopefully you see right away that we have to use the product rule, where this is our u and this is our v. So just using product rule, we know that y prime is u times v prime plus v times u prime. We know what u and v are, but we need u prime and v prime. So if u is e to the negative 5x and v is cosine 3x, well, this is the section on chain rule, so we're probably going to have to use the chain rule. So you want to think of the outside function and the inside function. Well, cosine, like think about on your calculator, it would put that in parentheses. So 3x is definitely the inside function. I guess I'll let that be my w, or maybe I'll think about using the function notation again. So the g prime of f of x. So remember, we take the derivative, so this cosine is the outside, 3x is the inside. So v prime, so it says, first take the derivative of the outside, but leave the inside alone. So what's the derivative of cosine? Well, it's negative sine, but leave the inside alone. Then at the end, multiply by the derivative of the inside function. So what's the derivative of 3x? That's just 3. So we get negative 3 sine 3x. And then I'm going to think of this. So think about if I were to type e to the negative 5x in the calculator. So I do second e to the negative 5x. And the way our calculator, I can't put an x in there, like I can with the graphing calculator. I can put like an x there. But so say I had an x here, then I'd have to close parentheses. And you could see that obviously this is in parentheses, so that would be my inside function. So this is like e to the negative 5x. So this part is my inside function. And the e part is my outside function. So u prime, so when you have this composition, it says take the derivative of the outside, leave the inside alone. So what's the derivative of e to the x? Well, it's just e to the x, right? It's its own derivative. So I still have e, but I leave the inside function alone. Then at the end, times the derivative of the inside function. What's the derivative of negative 5x? That's just negative 5. So I get negative 5 e to the negative 5x. Okay, and so now we can plug everything into the product rule. So y prime is u, which is e to the negative 5x, times v prime, which is negative 3 sine 3x, plus v, which is cosine 3x, times u prime, which is negative 5 e to the negative 5. And technically you can leave your answer like this. A lot of times what I would do is I would see, oh, they both have e to the negative 5x, so maybe I'll factor that out. Maybe I'll also factor out the negative since they're both negative. So y prime would be negative e to the negative 5x. And so then what would be left would be 3 sine 3x plus cosine 3x times 5. Or 5. Okay, I just kind of want to give you like the little shortcut rules for e and like the trig function. I'll do like cosine or sine. So suppose y equals e to some function of x. It's not just plain old x, so it's e to some big function. Then y prime, so these are kind of shortcuts for these two types of functions, e and then cosine or sine. So y prime is whenever you have e to a power and take the derivative, you always get e to that power back. So you're automatically getting e to the f of x back, and then at the end, you multiply by the derivative of the power. Depending, if you have more than one term, then you should put this in parentheses so that it would distribute the e. And then what if y equals cosine of some function, or y equals sine of some function? We'll call this g. Then y prime says take the derivative of the outside, which would be negative sine, leave the inside alone, and then multiply by the derivative of what you're taking cosine of. So if it was just like a number times x, like it was here, then you just know you're going to get times 3 at the end, right? So the derivative of cosine is negative sine 3x times 3. And similarly for sine. The derivative of sine is just cosine, leave the inside alone, and then at the very end, multiply by the derivative of the inside. The e shortcut is probably the most useful. You always get the exponential back, but then at the end, multiply by the derivative of the exponent. Okay, one more problem. Most of the problems on the test, I'm going to tell you you don't need to simplify at all, except for one or two. And I'll tell you which ones I want you to simplify. This problem 26, this is going to be one where I would expect you to simplify. So first, I know I'm going to use the quotient rule. I am also going to use the chain rule because I have parentheses to a power. So first I'm thinking of this as my u over v. And so g prime, start at the bottom, right? So v times u prime minus u times v prime all over v squared. Okay. So actually, let's go ahead and write u and v up here. So u is y minus 1 to the 4th. V is y squared plus 2y to the 5th. Parentheses to a power is probably, especially when it's a polynomial inside parentheses, that's one of the easier applications of the chain rule. It's what we did on the first page, right? So you bring the power that's on the parentheses down in front. So 4, leave the stuff inside the same, subtract 1 from the power, and then multiply by the derivative of what's inside parentheses, which in this case would just be 1. So let's look at v prime. So first, bring the power down. So 5, stuff inside stays the same, subtract 1 from the power, then multiply by the derivative of what's inside parentheses. So it would be 2y plus 2. Okay, let's plug all of that stuff into the quotient rule. So v is y squared plus 2y to the 5th times u prime, which is 4 times y minus 1 cubed. You don't have to write times 1. Minus u, which is y minus 1 to the 4th, times v prime, which is this, all over denominator squared. Okay, so here's how you simplify something like this. First, I'm going to do the denominator. Parentheses to a power, you just multiply exponents, right? So y squared plus 2y to the 10th. In the numerator, You don't want to multiply stuff out. You want to factor what they have in common. So I see they have y squared plus 2y here and a y squared plus 2y there. Let's think about like an easy algebra problem first. Like, what if I gave you 5x to the 4th minus 15x to the 7th, and I said factor that. So think about, what could you factor out in front? Well, they have a 5 in common, and then what power of x would you factor out? So you factor out 5x to the 4th, right? And you'd be left with 1 minus 3x, and what power here? Well, if you're taking away 4 of them, then that means 3 are left. Right? So you factor out the smaller power, right? Between 4 and 7, you factor out the smaller. So I have y squared plus 2y to the 5th and y squared plus 2y to the 4th. So I factor out the smaller power, y squared plus 2y to the 4th. Okay, but we also have y minus 1 here and a y minus 1 there. But just like before, you factor out the smaller of the two powers. So factor out y minus 1 to the 3rd. Okay. And then if there are constants to factor out, you can do that now or you can do it later. I'm just going to focus on the parentheses here. So I'm going to say what's left in each piece of the numerator when I've taken out what they have in common. Well, I've factored out 4 of the y squared plus 2y factors, which means there's 1 left. There's also a 4 left. But all 3 of the y minus 1s got factored out. So nothing is left there. Minus, okay, there's y minus 1 to the 4th, but I brought 3 of them out in front. So there's still 1 left. There's a 5 left. Y squared plus 2y, I factored out all 4 of them. So those are completely gone. There's also this 2y plus 2 left. Now you want to simplify inside these brackets. So I'm going to distribute the 4. I'm also going to think of, well, I'm going to multiply these two together and then do FOIL. So if I multiplied those two together, I'd get 10y plus 10. And then we'll do FOIL there. The other thing I see is that I have y squared plus 2y to the 4th and y squared plus 2y to the 10th. So there's going to be some cancellation there. Right? So these 4 factors will cancel 4 of those, so that means 6 are left. Right? And the y minus 1 cubed just stays there. Okay, so I have 4y squared plus 8y minus, so if I do FOIL here, so y times 10y, 10y squared. Outsides would give me plus 10y, insides would give me minus 10y, so they cancel. And then minus 1 times positive 10 would be minus 10. And then just think of distributing the negative and combining like terms. So 4y squared minus 10y squared would be negative 6y squared. Plus 8y minus negative 10. I am going to factor out a negative 2 from this and see if I can factor what's left. And we're just going to put the negative 2 all the way out in front. So that would be 3y squared. If I factor out a negative 2, that would be minus 4y minus 5. And I don't think this will factor. 3 times negative 5 is negative 15, and you can't get factors of 15 negative 15 to add up to negative 4, because it's just 1 and 15 and 3 and 5. So there's no way to get a 4 from those. So this won't factor. So this is as much as we can do to simplify that. Okay, the rest of the problems are done in the second video, and I might talk about using a graphing calculator, but remember, you don't get to use a graphing calculator on tests. It's good to use to check your homework if you have one. You can graph like tangent lines along with the graph and make sure that it looks like it's actually tangent to the graph, but that's just to check your work. You don't get to use one on the test. And then that video goes through to the end of the section. All right.